Hello, thank you for joining the second of our 4 sessions in our webinar series entitled Bioprocess Workflows That Win. We're excited to share with you today what differentiates Repligen as a solutions provider in the bioprocessing market and the benefits of the impactful technology solutions we bring to the market. Before we delve into tangential flow filtration with real-time process management topic, I want to make a short introduction to Repligen. Repligen has a track record of developing, launching, and supporting disruptive technologies, having brought 10 novel technology solutions to the market since 2017, leading to a 5-year growth rate in the company of 41%. In general, our technology platforms bring efficiency, yield, and productivity gains to biomanufacturing. We have developed technology leadership in multiple areas, including upstream intensification with Excel ATF and cross-flow TFDF technologies, downstream processing with Opus prepack columns, affinity ligands and resins, Tangenics flat sheet cassettes, and hollow fiber modules. Also in chromatography and TFF systems. In addition, with at-line and in-line advanced analytics with Solo VPE and Flow VPX slope spectroscopy technology, which we'll be discussing in more detail today. And finally, with total fluid management solutions that enable single-use bioprocessing. Our technology journey has evolved over time to offering fully integrated solutions. We start with differentiated consumables, then add standard and custom flow paths, and then that interface with our differentiated scalable chromatography and TFF systems that include advanced analytical technology for process monitoring and control. This complete solution renders an integrated technology solution for both upstream and downstream manufacturing. Importantly, our technologies serve many markets, from traditional modalities, including recombinant proteins and vaccines, to new modalities, including cell and gene therapy and cultivated foods. Some quick housekeeping before we get started. This webinar is being recorded for those who couldn't join us today. The on-demand video will be available at repligen.com next week. Please ask us any questions that you may have throughout the presentation. We also value input from our customers, so we have 2 polls today. The first poll is active now, and the second poll will be active after the webinar. You can ask questions and answer the poll questions using the Q&A and poll tabs located under the video player. And with that, I'm excited to hand over to Derek Carroll, a director in our R&D group, who will walk us through the benefits of inline concentration controlled tangential flow filtration.
All right, thank you, Christine. So yeah, my topic I'll be presenting is accelerating your UFDF process using the only inline concentration controlled TFF system. Our agenda will be looking at market needs and challenges, highlighting some of the new capabilities of the system, a technical overview looking into some of the data that we've collected with the system, and then at the end, we'll spend some time on questions if anything comes up. So as we looked at the market needs for our product, we identified the top ones for biological manufacturing. And what we saw for new product development areas of interest was the top one being real-time inline product sampling and testing, followed by automation instrumentation, and then followed by continuous bioprocessing, design of experiments, PAT, and analytical assays. So when we were deciding how to focus our resources and what kinds of products we wanted to develop to meet our customers' needs, we really felt like this was one of the best places for us to focus to meet some of these top needs. The other area we looked into was what we're seeing very common and becoming more common was high concentration MABs. And by high concentration, we're in the above 100 mg per mil range. And we've really seen this trend start to become much more common in the industry as more and more therapies are looking towards subcutaneous injection at home use versus need to go into the clinic for an infusion. So we really wanted to make sure that our system was able to address that need and be a manufacturing system that could be used for meeting those kinds of high concentrations. Although it was developed for MAB and that was really the focus, there have been a lot of other applications in gene therapy space where we've started to investigate use of this system. So we've investigated use with AAV, pDNA, mRNA, oligonucleotides, and VLP, virus-like particles. So if there are other applications outside of high concentration MABs, we've also had a lot of success looking into some of those. So although they're still currently in the investigation early stage, wouldn't shy away from thinking about using the system if you did have one of those types of applications. Okay, so taking a look at the 6 typical steps of a TFF process. So typically we see a CDC process, so an initial concentration, diafiltration, and then a final concentration. So typically what we see is first the protein is concentrations determined offline before you even start your run. And then you'll do pretty typical mass balance type of process where you determine concentration factors based on your starting volumes and try to calculate out where you're going to end up, and then run the process all the way through, and then hopefully you end up with a concentration factor that you calculated, and you confirm that by doing a final concentration determination, again, offline. So if that ends up not meeting exactly where you want to be, that requires either dilution if you've over concentrated, or potentially even a rerun of the process or additional processing time to continue concentrating. So we think we can help a lot with that by now actually controlling and measuring continuously over the course of the run. You always know exactly where you are, and the system's actually controlling to hit that target concentration. So current TFF challenges that we see on the market. So of course, as I just mentioned, being mass dependent, it's highly dependent on the accuracy of those scale measurements and the accuracy of your setup. So that could be things like making sure the correct weights are on the scales, you've taired properly, you've primed properly, and are perfectly set up to run that process out to the end. It's also a fragmented process, so you're in multiple ways. So one, you're needing to take measurements, go back and run, take measurements again, versus having them all in line. You also have fragmented data set locations where you have a data set location for your offline measurement and then a totally separate for your TFF run. And then those need to be unified afterwards to record your data from your runs. We also see a lot of variability. So we see run to run because of the mass dependence. We do see some inconsistent results. And then more severe risks of error. So like I said, the volume and hold-up volume calculations, dilution steps after the fact. So that is already introducing some amount of variation before you even take a measurement if you need to dilute. And then there are other types of errors that can happen in TFF runs. Examples, some extra weight being put on the scale and triggering some event if it exceeds your set point. So all of those things are present in TFF today, and things that we think we can address with this new system. So I'll highlight some of what we've actually been able to come up with. It is a PAT-driven TFF process. So We've unified two existing Repligen systems. So the CTEC FlowVPX system, which is an inline uv-vis spectrophotometer, using variable pathlength technology, so the signal will not saturate. And then our crossflow KR2i system, which is our TFF automation system. It's been on the market for a very long time and used in many downstream lab processes. Now with those two unified together, we can take the functionality of the FlowVPX to measure in line and then add that to the ability to take control of your process with the crossflow KR2i. So the FlowVPX, a little bit more about that. So it's a inline variable pathlength spectroscopy. It allows for rapid data acquisition. It generates 12 QC grade concentration measurements in 1 minute. So that's 5 path lengths in 5 seconds. This allows for much better accuracy, and it also allows for a very broad dynamic range. So we can see concentration measurements down 0.1 mg per mil all the way above 300 mg per mil without any dilution, able to measure everything directly in line. How that works, so compared to traditional UV spectroscopy, the main difference is in traditional UV spectroscopy, your path length is fixed. That will be dependent on the geometry of your cuvette or whatever inline piece of equipment you may have, whatever that fixed path length is, just based on the geometry. And then what's variable is, and unlocked is the concentration. So how you vary that concentration to get something accurate is you would have to dilute. And then once you see that that is falling within, the absorbance is falling within the linear range of the spectrophotometer, then you can apply that dilution factor back and calculate what your correct actual concentration is of your sample. What's unique about variable path length spectroscopy is it actually unlocks that path length variable and your concentration is a fixed value. You don't actually need to do any kinds of dilutions. You don't need to do any kinds of calculations. There will be the ability to change the path length. So that happens by adjusting a fibrette, which is applying a light source, and adjusting that position will allow for accurate measurement without any need for dilution. So yeah, we can see how does this inline variable path length technology work. So same concept as what we saw on the last slide, but actually now applied to an inline measurement. So as the material is flowing through your FlowVPX, it's continuously measuring that changing concentration throughout a process. And then a little bit more about the KR2i. It is our turnkey benchtop TFF system with walkaway automation. By walkaway automation, we mean there are 13 automated process control modes. You can also control things manually, but you will always be able to run whatever process you need to meet your PD needs and get your expected result without the need to intervene. Robust processing, so there's a very wide range also for the process volumes. We've gotten holdups down even below the 10 milliliter range all the way up to the 10 liter range. So it really covers a lot of what you would need for your lab and process development stages. Minimizes risk. We also includes a lot of the components for our ProConnex custom flow paths. So all of the tubing, the reservoirs, whatever you need to actually run your process, it's all purpose built for running your TFF system. And allowing all of that, giving all of those components in a kind of modular fashion allows for a very flexible configuration. So whatever you need for your process, you can mix and match and come up with the right combination of those accessories to get you exactly what you need. Okay, now getting into the technical overview, we'll get into some of the data. But first, we'll just take a quick look at what a traditional UFDF setup would look like, and now what that would look like with a FlowVPX added. So we have a picture up at the top. You can see what this would look like in reality, and then also on the piping and instrumentation diagram, you can see where all these things would fit in. A lot of this is going to look very, very common for a traditional CDC. You're going to have your feed tank, your filter. It's going to come through into your permeate tank. You have a buffer tank and a diafiltration addition pump for your diafiltration stage. The main addition here is the FlowVPX, and so the FlowVPX we would put in between the feed tank and the feed pump. And the reason for doing it there is that's the most accurate representation of what the concentration will be within the entire feed tank, right at that outlet coming into the feed pump. Okay, so the main thing that we really needed to develop to bring these two technologies together is the software. So the software, it allows for real-time process management. So we're calling it the CrossFlow RPM software. It still has all the familiar functionality for TFF automation control, but it now enables that inline concentration measurement. Gives real-time overview of every step along the way, graphs all the data, charts everything. So it's all in a single data location. And then it is still flexible plug and play technology for custom needs. And of course, it also has the functionality needed to operate the FlowVPX within a single software. All right, so now getting into some of the data that we've collected in our runs. So this is a process CDC, as we've mentioned before, for a typical UFDF run. We are using the FlowVPT device and measuring or setting concentration as the endpoint for our concentration modes. Diafiltration is still a traditional dia volume as measured by the scales, but we're able to actually set concentration as our set point. Okay, so in this video, we can actually see what happens as we start a run. So in this particular setup, we have a vacuum addition that will pull in feedstock. The recirculation vessel will maintain a constant volume up until that's depleted. And we can actually see an inflection point right as the feed tank empties, where the concentration rate goes up, and then it will continue concentrating up until it meets our target concentration. Next, we progress into the diafiltration stage. At this stage in the process, the buffer addition pump will turn on and it will maintain constant weight on the scale. As we can see on the chart, the VPX is measuring a constant concentration as all of the target molecules being retained, and it will continue running up until the point the prescribed number of dia volumes have been reached. Then lastly, we'll move into the final concentration stage. At this point, no additional buffer is added, and we are drawing down the volume in the recirculation vessel right up until it reaches that high concentration. And you can see bottles starting to empty, volumes are getting very low, and then all the way through to the very end of the process, we're hitting the target concentration within just a few % of the target. Okay, now taking a look at another run, so very similar setup to last time, but comparing what would be a more traditional mass balance type of process to a process fully using inline analytics. So instead of using concentration factors and diafiltration volumes, we're using target concentrations and using conductivity in this case for diafiltration. We're doing a buffer exchange for two solutions with different conductivity values. So we're able to set that as a target endpoint. And then, of course, for the final concentration, also using the VPX. What we see for the results, so there's on this, there's two axes, one for the concentration measured and the other for conductivity. In the mass balance, we can see based on where the targets are, the lines in red for C1, C2. In both cases, there was overconcentration. Going back after the fact, it was determined that there was just very minor calculations in terms of holdup volume and I think not perfect tearing of the scales as well. But still a result that would traditionally be seen as getting what you needed, and you just do a secondary dilution to get to your target. Versus now using inline analytics, we're hitting those targets within just a few percentage points. No need for any kind of secondary dilutions or additional processing. And the other thing we see looking at the conductivity axis, we're actually hitting the conductivity that we need to know that the buffer exchange is complete much more quickly by using the inline analytics versus dia volumes. We've already fully exchanged, the conductivity is already hitting the target, but it continues marching along as it goes towards the prescribed number of diafiltration volumes. So just a lot more control over your process, much more accurate results, and also the ability to know where you are at every step of the way in your process. So we took a look at consistency across platforms from these experiments. So we took measurements, of course, with the FlowVPX in line. We were measuring the entire time. We also use the Solo VPE, which is an offline system for still using variable path length. And then we use fixed path length technology doing dilutions to measure concentration as well. And we saw good alignment between the three. So really data that you can trust, data that you can use across your process. Okay, so now taking a look at where this fits in with our overall products. So it's really an integrated solution for lab development. You have that capability to not just have the pump, not just have the analytical instrument, but we also offer all of the filtration modules, whether it's hollow fiber or flat sheet. We supply all the components you need in your flow path. So we do offer standards if you just want to get up and running, or we do offer custom if there's something a little bit more unique that you're doing and you'd like to buy a pre-assembled flow path. And we are also seeing this just as the beginning. So the KR2i is our peristaltic lab pump. We are going to be expanding this to our FS15 diaphragm pump later this year. And then, of course, we're looking to only grow from there. We'll go up in scale and apply this type of technology across our entire range of systems. So yeah, the KR2i system, now enabled with the RPM software and the power of FlowVPX, allows you to strengthen your process control, increase efficiency, and then reduce your process risk as you may run into any kinds of issues. All right, thank you. Really looking forward to seeing how everyone's going to use this, thoughts on it. And yeah, I'd like to turn it back over to Christine for any questions we might have.
Thank you, Derek. Let's transition now to questions that our webinar attendees have. So the first question today is, what is the difference between the Repligen system and inline UV sensors from other vendors?
Sure, yeah. So the primary difference between the other inline UV sensors that are on the market from other vendors is those are typically fixed path length. So this Flow VPX device is enabled with variable path length technology. So the signal won't saturate. You can use a very dynamic range for concentration, which makes it ideal for a UFDF process where you're actually concentrating a molecule.
Excellent. And somewhat related, right? When we're working with very high concentrations of a given modality, has there been any work with um, looking at reading the concentration with very high viscosity solutions?
There has, yeah. So the Flow VPX is not sensitive to viscosity. If there's some turbidity in the sample or color, we may address that through built-in scatter correction, but viscosity isn't one that we really worry about. So as long as your UFDF process is running today with kind of a standard setup for flow path filter, and is usable with one of our standard KR2i setups, it's possible to use it with the Flow VPX, even if it is a high viscosity, high concentration application.
Excellent. And thinking about the diafiltration step, is there mixing required during that portion of the protocol?
Yeah, so yeah, it's a good one. So actually, mixing is important for this process, and as I mentioned during the presentation, we put the Flow VPX right at the outlet of the reservoir going into the feed pump. So good mixing is important to make sure that you're getting something that's representative of what the concentration in the feed vessel is. And actually, a unique capability of this system is if you did have polarization due to poor mixing, even short circuiting, where the retentate was flowing directly back into the feed, causing more kind of a higher concentration short circuit, that's something that the system can identify, and you would be able to see it's going at a concentration rate that's much higher than is even theoretically possible. That's a good indication of a problem. So having that real-time monitoring does allow you to identify those types of issues with your process and hopefully intervene and solve them before they lose a batch.
Excellent. And also related to the diafiltration step, is the addition of the diafiltration buffer controlled manually by the user during the run, or is there an automated calculation based on the concentration input or output?
Yeah, so it's not manual, but it's also not controlled by concentration. So the way that the system automates diafiltration, it is still based on the weights measured on the scale. So as you're permeating material, you're adding that same amount of your buffer if you're doing a buffer exchange to keep that level in the tank the same. So that's the automation there. Endpoint control, as we mentioned in the presentation, that is something that you can use conductivity for. So there are other ways to control that set point, but it is weight based that it will control the diafiltration step in the buffer addition.
Perfect. And with respect to the product concentration control, can we control to specific concentration ranges with a specified minimum and maximum?
So as it works, it's really based on single point. There is, of course, a little bit of variability. That's something that we did study quite a bit during the development of the system. Generally, we found it's very, very repeatable. It will typically fall within the -0, so it really doesn't under concentrate to +5%, and that's because there's a little bit of concentrated material in the retentate line at the end of your process that needs to be mixed through. So we do see slight amount of overshoot. And there's a couple of things that can affect that variability depending on exactly what your starting condition of your material is versus where you're trying to get to at the end, as well as some of the run parameters. But still a very, very tight range, much better than what we would expect through mass balance. But kind of the most important thing, I think, is if you are running the same process time after time, you can expect very, very similar results. So you'll typically fall within whatever ranges you would have for min and max regardless. And even if you didn't, you might be able to account for that pretty easily and have it fall within that range in subsequent runs.
Excellent. Okay, maybe a question regarding the positioning of the flow VPX sensor. Sorry. So does it make more sense to use the flow VPX sensor in the feed line or in the retentate line?
Yeah, so it does make more sense in the feed line. So if you think about what's really happening in a UFDF process, you're flowing material out of your reservoir, you're permeating a certain amount of material across your filter membrane, and then a more concentrated material is flowing back through your retentate. So what's in the retentate line will be more concentrated than what's in your reservoir. So as it flows back in slowly, it brings the average up as you're continuing the concentration process. So the most accurate representation of where you are in your concentration is going to be directly on the feed line and not the retentate line.
Excellent. And then another, measurement technology related question. So, does the VPX use disposable fibrettes? And have you seen any challenges with protein absorption onto the probe during processing? And if that does exist, can it be recovered with a CIP procedure?
Yeah, so the fibrettes are replaceable. They are reusable, so they don't need to be replaced every time you do a run. But they are replaceable. If there was anything with preventative maintenance, you would need to replace your fibrette. Um, there can be some deposits of protein during processing, so there is a cleaning step that's required between runs to make sure that none of those deposits are there affecting the signal. So we do recommend a CIP. Sodium hydroxide will remove any of that material, and you'll be ready for your next run.
Excellent. And also related, the Flow VPX system looks to be stainless steel, reusable, right? Is there a single-use version planned for the future?
There is a single-use version planned for the future. That is in development, and yeah, it's something definitely to look out for. Generally, for lab applications, we've found the reusable works very well, but that is a frequent question we get from our customers looking to have a single-use option, and it is something that we're in the process of developing and expect to have on the market relatively shortly.
Excellent. Next question. So is there a minimum process volume using both the VPX and the cross-flow systems?
Yeah, it's a
Feed volume.
good question. Sure, yeah, it's really a question around holdup, and so it's highly dependent on the details of your process and also of the design of your flow path. So in some applications, you can design a flow path to be very, very low holdup in the realm of just a few milliliters, sub 10 milliliters. So depending on what concentration factors you're starting or you're trying to achieve based on your starting volume, you could imagine that would get pretty low. But it's highly dependent. So what I would say more than anything, if you're interested in seeing if this can be used in your process, don't hesitate to ask. We can help out with flow path design, and we've been able to find designs and configurations that work for a lot of applications, even those that have very small starting volumes.
Excellent. There's a few questions related to scalability, right? So maybe you could talk about how the real-time process management and cross-flow system technology can be used in pilot and GMP manufacturing, and then maybe also highlight how we scale, right, in terms of piping sizes, piping design, with those considerations.
Sure. Yeah. So this system in particular is meant for the lab scale, and the RPM software is at this time meant for use with the KR2i. So right now we're at the lab scale with this particular system. We are expanding that, as I mentioned in the talk. The FS15, our Quattroflow lab system, is going to be launching later this year. We will continue to implement this technology across our range of automation systems in the coming years. But that being said, the FlowVPX is already very much scalable and used in pilot GMP across a variety of different scales. So we do offer a range of flow cells. So we have the 3 millimeter flow cell for lab, 10 millimeter from that process development up to pilot scale, and then we even have a 20 millimeter as well. So there's a wide range of sizes that we can address, and the software that we use with the FlowVPX is meant for use in GMP types of applications. So 21 CFR Part 11 compliance is easily achievable with this kind of system.
That's great. And maybe you could just highlight how the inline concentration measurement or monitoring from VPX during TFF differs from traditional offline concentration measurements.
Sure, yeah. So typically we'd need to actually pull a sample at various stages in the process, typically done at the beginning and the end, and you hope you ended up with what you wanted when you measure at the end, and you have your starting point to calculate your concentration factors at the beginning. So main difference being that those samples aren't as necessary. You can actually just know where you want to end up and start your process. It also saves on volume, so you don't have to take as many samples. You don't have to use as much of a volume when you do take a sample. And even if, in some applications you might need to measure in the middle of a process, that also isn't necessary. So you don't actually have to stop in the middle, account for the missing weight if you're using scales in a mass balance type of operation. And so, yeah, it really simplifies that quite a bit compared to taking offline measurements.
That's wonderful. And if a customer already has a KR2i system, can that system be upgraded to include the FlowVPX technology?
It can generally. So there are some much older generations of the KR2i. Generally, if it's a KR Roman numeral 2i, that's not something that we can upgrade. But anything KR2i numerical 2i should be upgradable. And we do offer that solution for anyone who's interested in making that upgrade.
That's great. So I think with time consideration, that's probably the last question that we'll answer live today. If you have asked a question, we will be reaching out personally to ensure that we provide a robust response to the inquiries that you've made. So thank you, Derek.
Yeah, thank you.
Okay, so with that, we have our second poll available, and would, as we noted, would appreciate your input here if you're so inclined to answer. And I want to highlight what comes next in our webinar series. But before I do that, I want to highlight that if you missed last week's webinar regarding upstream intensification, that content from Melissa Carpio is now available on our website at repligen.com. The presentation that Derek made today will be available in about a week's time on our website. And next week, we look forward to hearing about our fluid management solutions for single-use bioprocessing. So with that, again, thank you for your attendance, and please follow the content on our website if you need to at the end of the webinar. Thank you.